So it's a great honor for me to introduce Professor Schoen from Stanford University. He is a great mathematician does not need an introduction. And I just want to mention two things which are related to me personally. One is about more than 10 years ago when I tried to ask Professor Schoen to be my postdoc advisor, I was so nervous to call him. So I decided to call in the weekend, very early in the morning, like 9 o'clock in the East Coast. I just want to practice the feeling of call him. And then when I my first call, and then someone answered the phone in his office. I was totally unexperienced. Yeah, from that point on, I know that one really didn't work hard, even though if you are a genius, you still did work very, very hard. Yeah. The second thing is that he and Professor Lian Sama is my mentor when I was a postdoc in Stanford. He also is responsible for set up a meeting for me with Professor Donaldson, who I enormously benefit afterwards. Yeah. Okay. Thanks.
Well, thank you, Shushang, for the introduction. I think you're exaggerating a little. I can't remember coming to my office at 6 a.m. on a Saturday. But, let's see. So, okay. So anyway, it's a real honor for me to speak in this conference celebrating Blaine's 70th. Birthday. I'm going to talk about a subject which actually, in the first part, I'll summarize some work which was very much influenced by early work of Blaine in the late 60s and 70s, having to do with minimal submanifolds, particularly minimal surfaces in spheres. And so, just to say a few words, recall that if you take a submanifold of a standard sphere, say the standard unit sphere, then the condition that it be minimal is equivalent to saying that the coordinate functions, that is in Rn plus 1, are eigenfunctions of the Laplacian on the submanifold. So that connection, so there's a sort of a direct connection between minimal submanifolds of spheres and eigenvalues. And in fact, the connection really goes deeper than that, and I'll describe a bit of that in the first part of the talk. So I'm first going to give an introduction to the problem and talk about compact surfaces. And in particular, I'm going to pursue this connection between eigenvalues and minimal surfaces in spheres. And then I'm going to show that there's a natural extension, or sort of really an extension of the theory to manifolds with boundary. In particular, I'm going to talk about surfaces with boundary. Then I'm going to describe some recent theorems that we have for the case of surfaces with boundary. So this is a joint work with Ilana Fraser of UBC. And there's a paper posted which includes almost all of what I'm going to say, with the exception of one result. And so so I'm going to look at the following extremal problem for eigenvalues. So let's suppose we take a smooth compact surface M, and then if we choose a Riemannian metric, then we have a set of eigenvalues. So the lowest eigenvalue is 0, and then there's the first non-zero one I'll call lambda 1, and then the higher eigenvalues. And so I'm going to be interested in the problem of thinking of the eigenvalues as a functional of the metric. And in particular, it's not so hard to see that if you fix the area of the metric, then there's an upper bound on, for example, the first eigenvalue, which depends only on the topology of the surface. Okay, so that suggests the following extremal problem. Suppose we consider metrics on the surface with area 1, then we can ask what's the metric which maximizes the first eigenvalue. Okay, and so there are a couple of obvious questions. Does such a metric exist? And if so, what can we say about its geometry? Okay, and so whenever you study a variational problem, the first thing you want to do is assume that you have a solution of the problem which is sufficiently smooth, and then you want to figure out what conditions it satisfies. And so that's not quite trivial to do here because of the fact that eigenvalues have multiplicity. And when the multiplicity changes, the eigenfunctions will not change continuously or smoothly, at least not smoothly. And so it turns out that the Euler-Lagrange equation for this problem is that if there is such a metric, then the multiplicity is always pretty large. It has to be at least 3. And the maximizing condition tells us that we can find independent eigenfunctions, u1 up to un plus 1, with the property that pointwise, if we take the sum of the squares, we get 1 on m. And so that this map u, which takes the surface to Sn, then is a conformal map. Okay, and that's equivalent to saying that the image surface, sigma, which is u of m, is a minimal surface in Sn. And so, moreover, it means that the metric g that we started with, the extremal metric, is just a positive constant times the induced metric from the Euclidean space. Okay? And so the interesting thing is that if you can solve this extremal problem with a smooth metric, then the eigenfunctions will give you a minimal, well, a branched minimal immersion of the surface into Sn, so that the image is a minimal surface, and the metric is essentially the induced metric on that surface. Okay, and so there are a few known results on this problem. So in principle, the results, the extremal metrics are known quite explicitly in the case for surfaces of non-negative Euler characteristic. And one of those, the case of S2, is a theorem of Hirsch that goes back to 1970. And so in that case, the constant curvature metric, or a constant curvature metric, uniquely maximizes the first eigenvalue, given the area is fixed. And then in the 80s, in the middle 80s, the problem was solved for RP2 in a paper of Li and Yao, which introduces the idea of conformal volume. And in that case, the proof uses the fact that RP2 can be isometrically minimally embedded into a sphere. There's an explicit embedding by eigenfunctions, quadratic spherical harmonics, into S4 from RP2, and that plays a key role in the proof of the theorem. Now, in the case of the torus, the problem was taken up by Nadarashvili in the middle 90s, and he proved that in fact the maximizer for the problem is conformally, so it's a flat metric on a 60-degree rhombic torus. So that turns out to be the unique maximizer. Let me just say that it turns out if you look for, so that this was a result of Elsevier and Elias, based on the fact that minimal immersions of flat tori into spheres can be classified. So Elsevier and Elias showed that if you look for minimal immersions of a flat torus into a sphere by first eigenfunctions, so typically the coordinate functions, the embedding functions, are not first eigenfunctions. But if you require them to be first eigenfunctions, they showed there are exactly 2 such minimal embeddings, and those are the Clifford torus in S3. So that's a square torus in the 3-sphere, and the 60-degree rhombic torus in S5. So there's an explicit minimal embedding of that torus into S5, and it turns out the 60-degree torus beats the Clifford torus in this problem. It has larger area and the same eigenvalue than the Clifford torus. Okay, and then it turns out for the Klein-Bottle, the story is somewhat more complicated, but also, again, in principle is completely known. So again, it uses work of Nadarashvili and then several other authors, which I've listed there. And it turns out in that case, there's a unique maximal metric, which is achieved by it's not a flat metric, but it's achieved by an S1 invariant minimal embedding of the Klein-Bottle into S4, which was written down explicitly, well, in terms of some special functions involved. Problem. And so let me just say that the last two cases, the case of the torus and the Klein bottle, are actually a lot harder than the first two. And in particular, they rely on the existence of a smooth maximizer. And so that's a theorem which is in this 96 paper of Nadarashvili, but nobody really understands the theorem well. So there's really sort of a question mark about that theorem. And one of the things I wanted to do actually was to give a more transparent proof of the existence part of the subject. So that's the case of compact surfaces. Let me mention one other problem that I think is really interesting for the compact case, and that's the question. So of course, if you take higher genus surfaces, it's going to be very difficult to. So even if you can prove the existence of a maximizer, it'll be difficult to characterize it explicitly. However, you can ask the question, what happens when the genus is very large? And so what we can do is, if we take a surface of genus gamma, then we can define a number, lambda star of gamma, which is the sup. So multiplying by the area here just makes this scale invariant, so that it takes care of the area 1 normalization. And then we can ask, so this is a finite number. In fact, it has an upper bound, which is given in a paper of Yang and Yao. It's bounded above by 8 pi. This means the integer part of gamma plus 3 over 2. So that uses a complex analytic argument, actually a generalization of the Hirsch idea. And then on the other hand, there's also a lower bound. So it was shown by Boozer that if you take any surface of genus bigger than 1, you can always find a hyperbolic metric on the surface whose first eigenvalue is at least 3/16. So it uses some eigenvalue estimates for arithmetic lattices due to Selberg to do that. So there's always some metric with lambda 1 bigger than 3/16. And so then combining that with the hyperbolic area, you can see that this lambda star has a lower bound, which is 3/4 pi times gamma minus 1. So in particular, it grows linearly. And so it would be certainly interesting to understand the correct linear growth rate of this function. So that's I think an interesting question for compact surfaces. And I mention it because we're going to do something kind of analogous in the case of surfaces with boundary. Okay, so I'm going to now make a segue to surfaces with boundary. And so I'm going to do it in the following way. So if I take a minimal submanifold of the sphere, it's naturally the boundary of a minimal submanifold of the ball. So we can take the cone over it, and it's well known that the minimality in the sphere is equivalent to saying that the cone is a minimal submanifold of Euclidean space. Okay? And so in particular, the cone being minimal means that the coordinate functions in Rn+1 are harmonic functions on the cone. And of course, they're homogeneous of degree 1 because it's a cone. So on the boundary, we have this boundary condition. So eta is the co-normal vector, the outward unit normal vector to the boundary. And so the homogeneity tells us that the co-normal, that the coordinate functions satisfy this boundary condition. So the derivative in the normal direction reproduces the function. Okay, and so there's a class of minimal surfaces which satisfy this boundary condition. So geometrically, that boundary condition is equivalent to saying that the surface meets the boundary sphere orthogonally. Okay. On the next slide, I'll say a little more about this class of minimal surfaces. And so the cones are a special class of what I'm going to call free boundary submanifolds. So those are minimal submanifolds of the unit ball, which are orthogonal to the sphere at the boundary. We're going to call those free boundary submanifolds, and they're characterized by the condition that the coordinate functions are harmonic inside, and they satisfy this boundary condition. So such functions are called Steklov eigenfunctions with eigenvalue 1. And again, in a couple of slides, I'll describe that eigenvalue problem in more detail. So so it turns out that in a similar way as surfaces in minimal surfaces in spheres are potential extremals for the eigenvalue problems, it turns out that these free boundary surfaces are also potential extremals, as I'll describe. Okay, and so let me say a little more about free boundary submanifolds. So if we take a a k-dimensional submanifold in the ball, we assume it's proper, and it meets the boundary orthogonally, then the condition that h is 0 is just the condition the coordinate functions are harmonic, Laplacian is 0, and then the orthogonality at the boundary is this condition that it just says it's equivalent to saying that the conormal vector is the position vector. So that's the free boundary situation. Before I talk more about the eigenvalue problem, I want to give some examples which are important for our results. And so the first example, of course, is just a flat disk through the origin. So if we take a k-dimensional disk in Bn, equatorial k-plane, then obviously that's a free boundary minimal surface. And in fact, there's one uniqueness theorem in the subject which is due to Nietzsche, I think around 1970, way back. And he showed that if we take a simply connected surface in B3, which is a free boundary minimal surface, then it's in fact a flat disk. So there's no non-trivial simply connected free boundary minimal surface in B3. Of course, if you go to higher n, there very likely are lots of those. Okay, and the second example, which is important for us, is the critical catenoid. So if you remember that the catenoid is the unique minimal surface of revolution in R3 up to scaling, and it's gotten by revolving the hyperbolic cosine curve about an axis. So that's the curve x equals cosh z. And then what you can do is consider a line through the origin which is tangent to the cosh, the hyperbolic cosine curve. And then we can draw a circle centered at the origin through the point of contact. And then we can revolve that portion of the catenoid around. And then we see that we'll call that the critical catenoid. So it's the unique portion of the catenoid which meets the boundary sphere orthogonally. And then I can rescale so that the radius of the ball that I'm considering is 1. Scale the problem. So I'll call that the critical catenoid. So let me just say that we expect that there are, if you allow 3 boundary components for minimal surfaces in B3, there should be an infinite number of free boundary solutions with genus tending to infinity. And so these haven't been rigorously constructed, but I think they probably can be based on sort of gluing methods. And so the idea would be to take the union of the critical catenoid, which I have drawn here, with the plane through the origin. That's an immersed surface with a circle of self-intersection, circle of double points. And so then the idea would be to regularize that by punching a lot of holes, so the Shirk-type regularization of that. And that should be possible keeping the free boundary conditions. It's a nice elliptic boundary condition. And so there's not a lot of rigidity for this problem if you allow more than 2 boundary components, one would expect. Okay, then another example which is important for us is what I'll call the critical Mobius band. And so if we think of the Mobius band as R cross S1 with an identification, so T theta goes to minus T theta plus pi, then there's a minimal embedding which can be written down just by fiddling with harmonic functions in separated form. And so it turns out that if we take 2 sinh t cos theta, 2 sinh t sine theta, then cosh 2t cos 2 theta, and cosh 2t sine 2 theta, then you can check that each of those functions is harmonic on the cylinder. It's invariant under the identification, and that the map phi is a conformal map. So you can check that the phi is conformal. So in particular, the image of phi is a minimal. In fact, it's an embedding of the Mobius band, minimal embedding into R4. And then, just as we did for the catenoid, you can look at the intersections of that surface with balls or with spheres centered at the origin. And it's not hard to see that there's a unique choice of T naught for which the restriction is a free boundary surface. In fact, it's embedded by first eigenfunctions in this case. And so again, we can rescale the radius to 1 and we get what we'll call the critical Mobius band. Okay? And so explicitly T naught is a positive solution of this transcendental equation. Okay, so I'm going to come back to those surfaces in a minute, but I want to first say a little more about the eigenvalue problem. So this is the what are called Steklov eigenvalues. So generally, if we take a Riemannian manifold with boundary, we assume that the boundary is non-empty, then there's a natural eigenvalue problem associated. Of course, the most standard eigenvalue problems that you probably know about are the Dirichlet and the Neumann problems. But there's another one which is actually in some ways more important, at least in terms of applications, and those are called Steklov eigenvalues. It's related to the Dirichlet to Neumann map. And so what one does is so this is an operator for functions on the boundary. So if we take a smooth function on the boundary, say, then we can take its harmonic extension. So we solve the Dirichlet problem. So that has a unique solution, assuming U is sufficiently nice. And then we look at the operator which takes U to the normal derivative of U hat. Okay, and so actually this models a physical situation where you have some body inside and you don't know what's in there. But what you can do is take an electric potential on the boundary. So you apply some voltage on the boundary, and then you can measure. So then that will produce an equilibrium configuration inside, but you don't know what's in there. You can then measure the electric force on the boundary, and that's the normal derivative. And so that's the idea of the physical idea of the Dirichlet to Neumann map. Okay, in this map, it turns out, although it's not actually a differential operator, it's a non-local integral elliptic operator, and it has a discrete spectrum. So it's non-negative definite as an operator on L2, the boundary, self-adjoint, and it has discrete spectrum. So again, there's a trivial eigenvalue sigma naught, which comes from just choosing a constant function on the boundary. So then that, of course, has a constant harmonic extension, and so its normal derivative is 0. And again, the first non-zero eigenvalue is the one we're going to be interested in. So we'll call that sigma 1. And just as in the case of Dirichlet or Neumann eigenvalues, there's a natural variational characterization of sigma 1. So the corresponding Rayleigh quotient is the Dirichlet integral inside divided by the L2 norm squared on the boundary. Okay? And so that turns out to be a good Rayleigh quotient. The critical points for that are harmonic functions inside which satisfy the Steklov boundary condition, that the eigenvalue condition that the normal derivative is proportional to the function on the boundary. Okay, and so you can do a lot of the same kinds of arguments, variational arguments that you do for eigenvalues on a compact manifold or for the Dirichlet and Neumann problems based on the variational characterization. So things like the Courant nodal domain theorem and things like that work well in this setting also. And so the thing about the Steklov problem is that if we take in fact the ball or as I've sort of indicated, you can take any cone manifold, and it's true that the Steklov eigenvalues inside are exactly the ordinary eigenvalues of the boundary. So in particular, if we take the unit ball, then the eigenvalues are just the integers k, and the eigenfunctions are the homogeneous harmonic polynomials of degree k. Okay, so the eigenfunctions are the same as the eigenfunctions on the sphere extended with the appropriate homogeneity. Okay, and that's actually true for any cone. So in particular, sigma 1 is 1 in the case of the ball, and the lowest eigenspace is n-dimensional. It's spanned by the n coordinate functions. Or the m, I guess I mixed up n and m there. Right. Okay, so there's a very classical eigenvalue estimate for Steklov eigenvalues, which goes back to 1954, which essentially we're going to generalize, and that's so the initial setting is a simply connected plane domain. This is the Weinstock, And so the theorem is that if you take sigma 1 times the length of the boundary, so that turns out to be scale invariant, then that's bounded above by 2 pi with equality only if the domain is a disk. So that's Weinstock's theorem. And the proof is reminiscent. In fact, it's really a precursor to the Hirsch proof of the, for the case of S2. And so what it, let me just sketch it here. It uses the Riemann mapping theorem. So you produce a conformal diffeomorphism from omega to the disk, and then you balance it. Okay, so the idea is that we're going to use the variational characterization of the eigenvalues. So in order to have valid test functions for the eigenvalues, we need to make them orthogonal to the constants on the boundary. Okay? And so we can do that by using the conformal automorphism group of the disk. So we can consider composing phi with conformal transformations of the disk, and we can arrange that the map be balanced in the sense that the average value taken with respect to the arc length measure on omega, right, is 0. Okay, and so we can do that. It's not so hard to see. And then, so in particular, let's just assume that we've already chosen a balanced Riemann map. So we can assume that phi satisfies this. So this is phi has 2 components, phi 1 and phi 2. Then we can then use the phis as test functions, and we get that sigma 1 times the integral of phi I squared is bounded by the Dirichlet integral of the harmonic extension. Well, in this case, the phis are already harmonic, and so that's actually an equality. It's the gradient phi squared, and then we just add them up, and we get that since the sum of phi squared is 1 on the boundary, we get that sigma 1 times the length is bounded by, that's the energy of the map, and it's a conformal map, so the energy is twice the area, and that's it's the area of the image, and that's the area of the disk, which is 2 pi. Okay. So it's a very simple argument using the Riemann map. Okay, and there are many, many papers which look at higher dimensional versions of estimates for these problems. I've listed a few of the authors here on the slide. Okay, and so what we're interested in doing is taking this in the direction of surfaces with boundary which are not simply connected, so sort of general surfaces with boundary. And the first thing we do in order to get that is we need to know that there's some upper bound for the Steklov eigenvalues, and in fact that turns out to be possible to do. So we had an earlier paper where we proved one of these bounds, and then Kokorev observed that there's actually a bound that doesn't depend on k, the number of boundary components. And so putting those two together, you get an upper bound. If we take a surface of genus gamma with k boundary components, say an oriented surface, there's also a version for non-orientable surfaces, which I won't talk about here. But then the sigma 1L is bounded by the minimum of these two guys. So the merit of the second one is that it doesn't depend on k, but it has a worse constant in terms of the genus. So this, when gamma 0 and k is 1, it just reproduces the Weinstock bound. In fact, the proof is really an extension of the same idea. But for in all other cases, we expect this to be a non-sharp bound. So the question we ask is, what's the sharp constant for other surfaces? In particular, what about for the annulus? Suppose you take a matrix on an annulus, then can you find the sharp constant? And in fact, let me describe the main theorems here. So what we're going to show, and the reason I talked about the critical catenoid is that we claim that the critical catenoid actually uniquely achieves the extremal for the case of genus 0 with 2 boundary components, that is for the annular case. And so in order to show that, we need to be able to characterize the critical catenoid. And so the first theorem, which I'll call theorem A, does that. It says that if we have a free boundary minimal annulus in Bn, actually for any n, such that the coordinate functions are first eigenfunctions, then the result is that n is 3 and sigma is the critical catenoid. Okay, so the critical catenoid is actually the only free boundary minimal annulus which is embedded by first eigenfunctions, first Steklov eigenfunctions. Okay, so that's theorem A. And then there's a corresponding result for the Mobius band. So it turns out that that Mobius band that I wrote down is also uniquely characterized in the same way. So if we take any free boundary minimal Mobius band in Bn for any n, then in fact n must be 4 and sigma is the critical Mobius band. And if I have time at the end, I'll describe the proof of those. Actually, it took us a long time to figure out how to do this. It's a rather interesting argument, I think. Okay, and so in particular, then we can use those together with existence results for maximizers to prove theorems about sharp bounds. So if I take, say, the oriented surface of genus gamma with k boundary components, then we can take sigma star to be the supremum overall smooth metrics on that of sigma 1 times L. And then Weinstock's theorem says that sigma star 0, 1 is 2 pi, and so we can understand what sigma star 0, 2 is. So the claim is that if we take any metric on an annulus, then sigma 1L is bounded by its value for the critical catenoid. And actually, equality holds if and only if m is equivalent to the critical catenoid in a precise sense. Maybe I won't. So of course, because harmonic functions are conformally invariant, you can't really recover the metric inside from the spectrum, and so you have to phrase the equivalent statement appropriately. But there's a natural way to do that. So let me just use the word equivalent here. Okay, and so in particular, sigma star of 0, 2 turns out to be a number between 2 pi and 4 pi. It's 4 pi, roughly 4 pi over 1.2. So you can compute that, at least approximate it, sigma 1L. Okay, and then theorem 2 is an asymptotic theorem. So again, if we take, say, surface of genus 0 with k boundary components, then it's probably pretty hard to really explicitly characterize the solution, but we're able to asymptotically give a sharp bound. So if we look at sigma star 0k, it turns out it's strictly increasing in k, and it converges to 4 pi. So we started at 2 pi, and then the critical catenoid was a little bigger than that, and the claim is that all of these things are less than 4 pi, and they actually converge to 4 pi as k tends to infinity. And so for each k, there's a maximizing metric, which is achieved by a free boundary minimal surface in B3, and the area of the surface is less than 2 pi. The limit of the minimal surfaces as k tends to infinity is a double disk. That means it's a disk with multiplicity 2 through the origin. And it roughly looks like, it looks like a doubling of the disk in the sense that you take 2 parallel copies of the disk and you join them by k boundary necks, where the necks, roughly, if you scaled the necks up, you would produce half catenoids. So you can think of the catenoid as a way of bridging 2 planes together. So if you take 2 planes close together, then the catenoid bridges those together. And then if you take this surface and cut it in half through with a plane through the origin, then you produce a pair of half planes which are joined by a bridge, and you see that is a free boundary solution. That surface is orthogonal to the boundary plane that you cut with. Right? So the planes are orthogonal, and this catenoid is symmetric, so the half of it will be orthogonal to the plane that you cut with. Okay, and so the claim is that's what the figure looks like, and so we don't really have a precise description of the surfaces. I mean, you would expect that these have a finite k-fold symmetry group, but we don't actually know that because we don't have uniqueness theorems in the setting. And so in particular, a corollary of that is that there are in fact lots of free boundary minimal surfaces in B3. In fact, there's at least one for every k of genus 0. And moreover, they're embedded by first eigenfunctions. Okay, and so let me describe a little bit about what goes into these results. Okay, and so there's an existence theorem. So actually, this is the result which is not yet in the paper. So we're pretty sure that we can do all of this, but this is a sort of hard. This is the analog of the Nadarashvili existence theorem for closed surfaces, and we have an approach to this which we're pretty confident about, and probably it has an analog for the closed case too, but it still isn't in the paper that I mentioned. Okay, and so the result is though that if we have actually this is not the existence result. This just characterizes a smooth metric, assuming that there is a maximizer. So suppose we have a compact surface and we assume we have a metric for which sigma 1L is maximized. Then the multiplicity is at least 2, and there exists a proper conformal branched minimal immersion by eigenfunctions to Bn for some n greater than or equal to 2. It's by first eigenfunctions, and it's a homothety on the boundary. So it's a conformal map, which on the boundary is an isometry or scaling. Okay, so that's sort of the uniqueness part for this. And so in particular, the induced metric from the minimal surface is equivalent to the extremal metric that we started with. Okay, so this is just the analog of the result I had on the second slide, which calculates the Euler-Lagrange equation for the problem. So assuming we have a smooth maximizer, then we can do this. So this actually is in the paper. It's kind of an interesting argument. It uses the Hahn-Banach theorem in kind of an interesting way. In fact, if I have time, maybe I'll describe it at the end. Okay, and so the hard part, the theorem which is not in there is the existence of maximizers. And so I'll say a little bit about it here. So the claim is if we take any k greater than or equal to 1, there's a smooth metric on the surface of genus 0 with k boundary components, which achieves the maximum. And so in the existence problems in either the compact or the case of surfaces with boundary, there are two steps. The first step is to control the conformal structure, right? So any metric determines a conformal structure, and the conformal moduli is a finite dimensional space. And so you have to be able to control the conformal structure so you don't have things like next pinching, or in this case of boundary components which shrink to 0 in length, or which come together conformally. And so a key step in doing that is to prove that these are strictly monotone. So it turns out sigma star 0k is strictly bigger than that, at least assuming this one is achieved. So the proof is by induction. If you assume you have a solution with k minus 1 boundary components, then you can show that when you punch a hole in it, so it's really just an asymptotic calculation that by punching a very small hole, you actually strictly improve the sigma star. So what happens roughly if you punch a hole of size epsilon is that the eigenvalue changes by something of order epsilon squared, but the boundary length increases by something which goes like epsilon. So it turns out that there's there's a result that says these strictly increase, and that keeps that precludes certain types of degenerations in the conformal structure. So that's actually a key step, and that is in the paper actually. So the conformal part is in the paper. So the sort of analytically difficult part is once you have control of the conformal structure, so you have a given background metric, the problem is then to produce a maximizer. And so in order to do that, you have to take some kind of weak limit. And so we use a regularization procedure to do that. So we don't take any old maximizing sequence. We do an approximate, we take a regularized problem and take a maximizer for that, which exists by elementary arguments, and then we take the weak star limit, and then we have to show that then there's a regularity theorem to show that that weak star limit actually comes from a smooth metric, and that comes from the fact that this regularized problem has eigenfunctions which you can handle in a certain way, and so you have to control the Hopf differential of the corresponding map. So this is really the hardest technical part of the work, and as I say, this is not actually yet in the paper. And then the rest of it. So once we have a maximizer, then it's easy to show that once we have really a weak solution of the free boundary minimal surface equation, there's a good regularity theorem for that, higher regularity theorem. And then one can show that the metric's actually smooth. And in fact, in this case, there are no branch points on the boundary either. So the extremals here don't. You can take the metrics to be smooth without singularities inside as well. Okay, and so there's the existence part, which is definitely a hard analytic part. And so once we have that, we can describe the proof of Theorem One, which is I've restated here, which says that the critical catenoid maximizes uniquely the sigma 1L. And so the way the proof goes is that you first use the fact that there exists a maximizer, right? So, and that maximizer arises from a free boundary minimal immersion of the annulus into the ball, and then we use the uniqueness result that I described, Theorem A, whose proof I may have time to get to at the end. Okay, and so that's how the proof goes. And the asymptotic statement when k is large comes from the fact that so first again you need the existence theorem. So there's a minimal surface sigma k, which is a maximizer for the problem, and then there's a crucial geometric property which is used for the nodal sets of eigenfunctions. So the eigenfunctions for these sigma k's are just coordinate functions, right? And so the nodal sets are the intersections of the surface with planes through the origin. So a basic property that these have, because of the genus zero property, is that in fact the nodal sets of the eigenfunctions are everywhere smooth in the interior. So every plane through the origin intersects the surface transversely away from the boundary in the interior of the ball. And so that's a key property that's used here. And what that implies is that the surfaces are actually star-shaped with respect to the origin. So back to my surfaces here. So of course the critical catenoid is star-shaped, but these surfaces also are star-shaped. You might guess that from the picture. So they're star-shaped, and that really is what enables us to understand the asymptotic limit. Okay, and so we have a coarse upper bound. So the coarse upper bound gives us an area bound for these surfaces, right? Because the sigma 1 is fixed, and the length of the boundary is actually twice the area inside for free boundary minimal surfaces. So you have an upper bound in the area, and then they're star-shaped. So the fact that they're star-shaped implies that they're stable with fixed boundary. So they're stable minimal surfaces in the interior. And in particular, there are curvature estimates, which one can use to take limits of these things. And so we can take a sequence which converges smoothly in the interior to a surface possibly with multiplicity. And in fact, the surface has to have multiplicity, one can show, because the topology, because k is going to infinity, it can't converge to a single disk. Okay, and then a little more work. Well, from the star-shaped property, it follows that in fact the multiplicity is 2, and in fact the limit is in fact a double disk. So again, the star-shaped property implies the origin is contained in the limit, and so the limit is a cone, so it's a plane, and then you have to show that the areas actually converge, so you don't have sort of concentration of area at the boundary, and that all works out. It uses monotonicity type results, and so we can then prove that the limit of the areas is actually 4 pi, and that is actually 2 pi, and that gives the corresponding result about the eigenvalues. Okay, so the picture of these is rather nice. If we take one boundary component, then we're in the Weinstock case of 2 pi. With 2 boundary components, we can explicitly find it. It's a little bigger than 2 pi. And then as k tends to infinity, these converge asymptotically to 4 pi, the sigma star 0k. So that's the idea of Theorem 2. And the Mobius band is similar. Again, we have to prove the existence of a maximizing metric. So we have the existence, and then it's given by an immersion by first eigenfunctions, free boundary immersion, and then we use the uniqueness result, again, to argue that it's the critical Mobius band. Okay, I have a few minutes, so let me describe the proof of Theorem A, which is I think is rather interesting. So I've rewritten the theorem here. So assume I have a free boundary minimal annulus in Bn such that the coordinate functions are first eigenfunction. Then the claim is that n is 3 and sigma is the critical catenoid. Okay, and so first of all, the fact that n is 3 actually just comes from a multiplicity bound. Okay, so it turns out that genus 0 surfaces with any number of boundary components have multiplicity bounded by 3. That's a consequence of the Courant nodal domain theorem. And so although actually this argument would work even if we didn't know that. So even if it isn't based on codimension 1 actually. But nonetheless, we can simplify notation a little to use that. Okay, and so then we can just parameterize the annulus conformally. So it's conformally equivalent to minus TT cross S1 for some choice of capital T. And then we look at the conformal killing vector field, that is the rotation vector field on the annulus. Of course, any annulus has a conformal symmetry. So typically, the conformal symmetry is not an isometric symmetry, right? And so what we want to show is that this conformal killing vector field d phi d theta. So we think of putting it into the ambient space. So it's a vector field. You think of it as a vector-valued function, if you like. And then the components. There are 3 components of it. The key step is to show that the 3 components of x are first eigenfunctions. That's the key step. And it turns out once you have that, you can fiddle around and show that x actually is a rotation vector field. So a rotation vector field, of course, the components are just coordinate functions, right? The coordinate functions are first eigenfunctions in this case, okay? And so the key is to show that the 3 components of x are first eigenfunctions. Okay, and so the way we do that is to introduce the following quadratic form. So if we consider vector fields y along segment, so y is not a tangential vector field. It may have tangential and normal components. Then we can look at the quadratic form, so q of y. So this is just the sum of the gradient squared of the components of y. So think of y as a vector-valued function, and then I'm subtracting the integral over the boundary of the norm of y squared. So I'll tell you in a minute why this is a useful quadratic form to look at. But the first observation is that because sigma 1 is 1, if the integral of y is 0 along the boundary, then this is a non-negative definite form. And equality holds if and only if the components are first eigenfunctions. That's just because, just from the variational characterization of first eigenfunctions. If y integrates to 0 on the boundary, then the form is non-negative, definite. Okay, and so the idea then is to so we look at this vector field x, and the idea then is, well, I mean, if it were true that x integrates to 0 on the boundary, then we could actually complete the argument, because x is actually in the null space of this form. So it's, again, just from the conformal killing equations, you can see that q of x, y is 0 for any y, provided y is tangential to the sphere at the boundary. Okay? And so it's actually in the null space of the form among vector fields tangential to the sphere. And then the quadratic form q also has a variational interpretation. Namely, it's the second variation of the energy, or half of the energy, provided, again, that y is tangent to the sphere. So the deformations of this for this problem are vector fields that are tangent to S2. So those preserve the flow preserves the ball. And so the idea then is to find sufficiently many vector fields y so that qyy is less than or equal to 0, and so that I can arrange the difference to integrate to 0. Okay, and so remember, x is in the null space of the form. So if qyy is less than or equal to 0, then q of that difference is also less than or equal to 0, because x is null. And so the idea is to find sufficiently many y with that property, and then it would follow that the components of x minus y are first eigenfunctions, and then, okay, again, you can fiddle around to then show that x is actually a rotation vector field. Okay, and so that's the key. Okay, so the question is, how do you find these deformations y? And so it turns out we couldn't really do that directly. So there's a sort of natural thing to try would be to use the conformal deformations of the ball to do it. So there are the right number of them, but we can't show that they actually reduce the energy. So we had to look for plan B here. And so what we were able to do is to, instead of looking at the second variation of energy, we were able to understand better the second variation of area. And so for area, of course, it's generally sufficient to consider normal vector fields. So that turns out to be a little easier problem. So generally, area is more unstable than energy for surfaces. And so it's a calculation that the second variation of area is this quadratic form. So if I take my variation to be psi times the normal, then this S of psi is the second variation of area for this problem. So if psi is 0 on the boundary, then this is the standard quadratic form for the second variation. And if psi moves the boundary, then there's an extra negative term that comes from the boundary there. So that's the second variation of area. And then, so this is for normal variation psi nu. So in this case, there's also a sort of natural Jacobi field, which is 0 on the boundary, and that's the support function x dot nu. So because of the free boundary condition, the normal is perpendicular to x, which is equal to the conormal on the boundary. So this x dot nu is a Jacobi field inside. It generates the generator of dilations, and it's 0 on the boundary. So x dot nu is in the null space of this area, of this second variation form for area. Okay, and so then there's a calculation. So it's a little bit of a tricky argument, but it turns out if you take any vector field in R3, then the corresponding variation field, that is, if you take v dot nu, so you think of that as a deformation, so then it turns out that is less than or equal to 0 always, and that's true for any v in R3. So in particular, you have this sort of built-in three-dimensional space of variations that reduce the area. So that's the key point. Okay, however, it doesn't do us any good for the eigenvalue problem because generally these deformations will not preserve the conformal structure up to first order. And so so the second variation of area will not be the same as the second variation of half of the energy. Okay, and so what we do to get around that is we consider adding a tangential part. So some of these variations will preserve the conformal structure. So remember, we're working on an annulus, so the space of conformal structure is only one-dimensional, right? And so we have a three-dimensional space of variations, actually 4 if you count the x dot nu, the support function. So in particular, a lot of those should actually preserve the energy. And so what we do is look at the problem of the question of whether we can add a tangential part, y tangential to y, so that it preserves the conformal structure, and of course is tangent to S2 along the boundary. Okay, and so when you look at so this involves a PDE for y, and not surprisingly, it's a Cauchy-Riemann type equation with a natural boundary condition, which saying that y is tangential to the boundary, and so it turns out the problem isn't generally solvable, but there's a one-dimensional co-kernel for the corresponding operators, a one-dimensional obstruction to the solvability, and again, that's because of the fact that sigma is an annulus. But on the other hand, we have a four-dimensional space of normal variations. We have the three components of the normal, and we have x dot nu. All of those, so on that space, the second variation form for area is negative definite, or non-positive definite. Okay? And so the idea is then to show that there's a three-dimensional subspace which actually preserves, which are conformal deformations, which preserves the area, and then for that, on that three-dimensional subspace, the Q is the same as the second variation of area and less than or equal to 0. And then because it's three-dimensional, we have to show that you have enough flexibility to subtract a y to make the integral of x minus y 0. So those are three conditions, because x has three components, x1, x2, x3. Okay, so that's the idea. It's a rather interesting argument, I think. It's in the paper that I posted, that I mentioned at the beginning. Okay, and so that's the proof. And then there's an analogous proof for the Mobius band. Again, the key for the Mobius band is, so now we're in Sn, so some high n. The multiplicity bound in that case doesn't give us 4, it gives us something like 6. And so we have to extend this argument to higher codimension. But again, it's the same basic idea. So the Mobius band has an S1 conformal symmetry, and we have to show that that's isometric. And it's the same basic idea for doing that. So once it becomes, once we have a S1 symmetry for the surface, then we can use sort of separation of variable techniques to characterize it, to show that it's actually the critical Mobius band, the one I wrote down. Okay, so that's all in the paper. So as I say, the only thing that's not in the paper that I described here is the existence theorem. Okay, so we think that's okay, and we're hoping to get that in quite soon. So I think maybe I'm finished, so maybe I'll stop there. Yeah.
Does this eigenvalue, if you fix the genus, is it always monotone?
Well, I mean, nobody has done that. I mean, so even for compact surfaces, I think that's quite likely to be true. So if that's true, and if all the existence theory works out, it would give you the existence of a maximizer for any genus. And so I think it's a question of how to sort of, assuming you have an extremal in one genus, how to add a handle in such a way that you get a slight improvement on the eigenvalue. Now, I haven't looked at that much because I'm trying to get this part finished up, but I have hopes that that's true. I think if you had that, then that would give you control of the conformal structures for any genus. You can then go by induction, and it would give you at least the existence of a maximizer. And then there may be hope of understanding the asymptotics of that sequence of minimal surfaces. But it's a lot harder because, of course, the areas go to infinity. So these are in big higher dimensional spheres, and so it's a much harder asymptotic problem than the one we solved. But yeah, that's a good question, and I don't know the answer.
Given a general Riemann manifold, when would there exist a conformal killing vector field? The existence?
Oh, usually not, of course. I mean, you know, you can always, if you take any manifold, okay, so you take a compact manifold. So let me tell you something I know. So if you take any compact manifold which is not the standard sphere, then you can always choose a metric for which the conformal killing fields are the killing fields. So the conformal group is then a compact group, and so then it's the question of a metric with killing fields. So I mean, generally, of course, if you have a compact group topologically smoothly acting on a manifold, you can take a metric and average it, and find a metric which is invariant. But yeah, I mean, these arguments, this problem that we're looking at is very much a two-dimensional problem. I mean, I don't think that it's going to be hopeful to try to do these extremal eigenvalue problems in higher dimensions, unless you restrict the class of metrics very substantially.
There's an obvious reason why you should target to be flat.
In this problem? Well, it's related to the fact that I mean, if you think of the eigenvalue problems, related to the fact that the eigenfunctions are harmonic inside, right? And so the map is a harmonic map into Euclidean space. Whereas in the case of compact surfaces, the eigenfunctions are not harmonic. That corresponds to the case of the sphere. So I didn't actually explain why, if you have a maximal metric, it arises from a free boundary minimal surface. But yeah, so maybe a good answer is if you compute the first variation. So if you think you have a maximizing metric, you vary the metric, and then you look at formally the first variation, then that being 0 tells you that the Hopf differential of the map is 0 inside, so it's conformal. And of course, it's harmonic because of the Steklov. And it also gives you conditions on the boundary. Okay, and so it's really understanding that first variation, which gives you this local theorem that an extremal comes from a free boundary minimal surface.
Okay. Helpful.